morning. Thank you. I know you could do better, but it's before lunch, so I'll give you a pass this time. My name is Harishankar. I am an IBM fellow within the IBM quantum team, and I'm focused exclusively on quantum safe. And you may be wondering, what is quantum safe? That is exactly what I'm going to talk to you about, right? But before I go there, I do want to set the stage that you have heard a lot of discussions around fundamental quantum computing and the advances thereof and all that. And you may have heard a speaker, Jamie, yesterday from IBM, who spoke about some of the work that we've been doing in that space. So I'm going to do a very quick level set of some of the key things that we have called out actually, this is something that we called out in the Quantum Summit that we had almost exactly a month ago. November 9th, if I remember right. And I'm not going to walk you through every one of these, but we made some pretty significant announcements that I just want to quickly run through. And the first is around the scale, quality, and speed, right? So we announced that we have a 433-qubit processor that we are going to be putting online by the end of the year. And this adds to the 20-plus systems that we have that are available to you to use. And we have been focusing on quality as well as speed to make sure that we keep addressing them and increasing them as the demand increases. Obviously, you have had a lot of discussions that talk about error suppression, error mitigation, and so we are addressing that as well. So there have been some significant advancements in that. And there are some things that we can talk about there as well. Now, with dynamic circuits, we find that we can create dynamic circuits, and all these aspects of quality, speed, error suppression, error mitigation, and dynamic circuits are all available in the Qiskit runtime, so they're automatically made available to you. And then we also wanted to call out that our quantum network, as everyone has called out, this is not a single-player game. It is an ecosystem game, and we are proud to call out that we have over 200 partners in that ecosystem as part of the quantum network, and collectively we are making significant progress. And the box 8 is what I'm going to talk about, which is quantum safe. So I'll skip that for a second. And then in order to help us achieve the maximum efficiency and throughput, we are also building in what we are calling quantum serverless and circuit knitting that enables us to optimally and efficiently execute circuits. And putting all of this together, we are looking at what we are calling quantum-centric supercomputing, which actually has an aggregation of these capabilities made available to solve customers' problems, right? Now, at IBM, if you look at the focus of IBM Quantum, you can look at it as two sides of the coin. One side is focused on fundamental quantum computing that the majority of this conference has been talking about. The other side that we recently began to focus on is on quantum safe. And you may say, what is quantum safe? Well, for that, let me start with the notion of modern digital cryptography. Every digital interaction that you have, whether it be booking tickets online, whether paying your bills online, whether transacting with your bank, or as an enterprise, if you're exchanging documents with your ecosystem partners or the government, you name it. Every one of these digital interaction is based on trust. Trust that transaction is going to be secure. And that security is guaranteed by the appropriate use of cryptography. And we have taken it for granted for so many years, and it pretty much works, right? Now, if you say, okay, I get it conceptually, what is this cryptography? Cryptography is nothing but math problems, difficult math problems that a classical computer or a quantum computer have a lot of difficulty solving, right? And you guys know this. And one of the key such algorithms is prime factorization, or math problems is prime factorization or integer factorization. And RSA 2048, one of the key protocols that is used in public key encryption, is based on a 2048-bit composite number. In case you're wondering how many digits there are in that number that you see there are about 616 digits. So if I told you 65 and find factors for that, you'll immediately come up and say 13 and 5. But try doing that for a 616-digit number. Even a classical computer takes years, if not hundreds of years, to solve that. That's the foundation on which asymmetric cryptography is based, and that's why we trust all these transactions and they all work. However, with Shor's algorithm, you know that can be broken. That's the fundamental problem, right? So the potential that Shor's algorithm can be applied in the future to break the foundations of cryptography is the challenge here. So you may say, wait a minute, what does that really mean, right? So what you see here is a set of asymmetric cryptography algorithms, right? Whether it is RSA or DSA or digital signature algorithm or ECC or Diffie-Hellman, whatever the case happens to be, they're all based on the similar type of problems, and they all get broken by Shor's algorithm. So all of the cryptography that you rely is out the window. Now, obviously, I shouldn't say all, most of the cryptography that you use is out the window, which begs the question, what is left? What is left is symmetric cryptography, which actually is affected by Grover's algorithm, but it's only offering quadratic speedup, whereas with Shor's algorithm, you are getting a exponential to polynomial shift, right? So you may say, well, I get it. However, based on all that we have heard in this conference and what you know so far, a quantum computer that is mature and capable of solving Shor's algorithm or applying Shor's algorithm to solve this problem isn't anywhere in the horizon. So RSA isn't going to be broken anytime soon. Why do I have to worry about it? Well, before I answer that question, let me establish a couple things. One, I've already talked about the fact that cryptography is pervasive. Every transaction we have, right? And you can sit here and imagine any transaction that you don't have an impact with cryptography. There may be very few, but pervasiveness of cryptography cannot be denied. Now, juxtapose that with the fact that whenever I say crypto here, please don't confuse that to cryptocurrency. That's not what I'm talking about. I don't want to keep saying cryptography, and my tongue doesn't roll well, so I keep saying crypto. So let me put that disclaimer out there. So many of the crypto systems that companies, our clients, have are somewhat complex, to say the least. They are made up of systems that they built, systems that they bought, systems that they are contracting with, and different cloud platforms that they're deploying things on, so on and so forth, and numerous partners they interact with. Every one of them has their own cryptography that you need to understand and remedy or address if you have to solve this problem. And how long is that going to take? Our work shows that it takes at least 5 to 7 years for large enterprises to complete that transformation. Why does it take that much time? Because many of them don't even know exactly what exists today. And then you've got to think about the budget of that, and then the work that needs to go on, and testing of it, so on and so forth. So 5 to 7 years is a reasonable time you can expect any enterprise to spend to address this challenge of broken crypto that needs to be remediated. Right? That's data point number one. The second is, we obviously have to store data for long periods of time for regulatory purposes and other reasons, right? So the data that you have needs to be protected as well. So there is a time sensitivity to the data that you have. That begs the question, so what can a bad actor do? What kind of nefarious actions can be taken? And keep in mind that whenever we say bad actor here, you may be thinking about, 5 guys in a garage or a basement trying to hack into things, or you may also be thinking about nation states that are bent on breaking into systems, right? I would say it's more the latter than the former, or a combination of thereof, biased more on the latter. What can they do? Well, it's fairly obvious what, when somebody breaks cryptography, they can do, right? Digital signatures are compromised, which means that, for example, if you're using a blockchain, the blockchain is either rendered weak, exposed, or broken. All of them are bad. Repudiation is lost. And the most important challenge is the last one that I call out here, which if you are able to sniff data today and save it on your hard disk, you don't need to decrypt it today. You can hang on to it for a while. And when a quantum computer of sufficient scale and maturity becomes available, you can decrypt what you have collected so far and then see if you hit the lottery or not. That's the fear, right? So this harvest now and decrypt later is the challenge that enterprises face. And that is the core of this quantum safe challenge that we fundamentally need to be concerned about. Many people compare Y2K to YQK, right? Cute little term, but there are a number of differences, and this is an important difference in that Y2K had definitely a finite time when things turned over, so you could do something about it. Here, we don't exactly know when that time is going to happen, so you need to be prepared for it. The second is there is no such notion of harvest now and decrypt later in the case of Y2K. So this is an existential challenge that we have today that we need to be very concerned about. And now you may be saying, okay, I get the challenge. I get the fact that it's bad. Now, when is this really going to happen? What are people saying? Now, this you may relate to. I'm not in the habit of speculating, so I'll call out a few key studies and data points that have been put out there. Dr. Michel Mosca from the University of Waterloo says that there's a 50-50 chance that RSA can be broken by 2031. NIST pretty much agrees with a similar timeline. A recent study that was published by the World Economic Forum in September of this year called out that the time zone 2031 to 2035 is a danger zone. Then you find a number of national security memorandums coming out of the White House and associated NSA guidelines that all call for 2032 to be the time by which all the vendors and systems need to be quantum safe. The bottom line is that time horizon, 2030, early 2030s, seems to be the time where things will hit the fan. And so we need to be prepared for it, right? And you may say, okay, wow, well, that's not too far away. I talked about 5 to 7 years of remediation time. We are sitting here in 22, 23, and there's really not much time to think about. That's why you see a lot of government memorandums, security memorandums coming out with a number of these dates and actions. In fact, the most recent one that came out said every government agency has to have an inventory by May of next year as to what their current cryptography landscape looks like. So that you'll see a lot of action coming out of this. And all this points to the realization that a fundamentally viable, scalable quantum computer is likely to be in our hands in the early 2030s, right? So what have we done about it? Do we have a solution to this, right? Now, I've scared the heck out of you with all of this, but then now I'm trying to turn around and probably reassure you that, well, NIST was working on this since 2016. They put out a competition to ask for algorithms that are quantum safe, that cannot be broken by classical as well as quantum computers. And so there were 80-plus submissions. Fast forward to July of this year, they went through several rounds of scrutiny, and I think after 4 rounds of scrutiny and assessment and evaluation, they came up and said there are 4 algorithms that they have selected on which they will build standards. They're continuing to receive and evaluate additional algorithms as well, but these 4 are going to be the first set that they're going to build standards on. And I am thrilled and proud to say that 3 of the 4 algorithms came from IBM working in collaboration with academia and industry partners. Right? So the 200 researchers that we have really earned their keep by making sure that our algorithms made it into the final set. And these are the 4. I'm not going to dive deep into it, except to say that the key points are we can't just look at these as replacement algorithms for what exists today, because the techniques are quite different. At the same time, you have to think about the fact that these algorithms have to work not only on a server farm where you have very limited constraints for memory, CPU, and bandwidth, whereas they also have to work on small IoT devices that exist deep in the seabed or 100 meters under the ground on an equipment or wherever they are put up with very constrained bandwidth, CPU, and memory limitations, right? So got to think about how to efficiently apply this. But one of the things we did was we made a bet that our algorithms will be selected. So we turned around and included these algorithms in our IBM systems, tape drives, in the IBM cloud, and more recently in the Z16 platform that we released, which is currently probably the first commercially available quantum-safe platform that exists. That entire stack is protected and is quantum-safe through algorithms that have been encoded into or are part of the underpinning of Z16. Now, that's only one part of it, right? How are we going to solve this? That's the bigger problem. I think, we believe, that while this can be a problem that can be solved one client at a time, we really need to take an ecosystem view. What I mean by that is, if you think about telcos form the underpinning of every enterprise in one way, shape, or form. Everyone uses the network. Everyone uses the connectivity that the network provides for any of the underlying communication that needs to happen. And so if we can form a consortium approach and address the challenges of quantum safe at an industry level, then everybody benefits. So in September of this year, we launched a task force, Post-Quantum Telco Network Task Force, in collaboration with Vodafone and GSMA, which is a standards authority. And as of now, we have about 40+ members who are part of that task force, and they're actively working on developing standards that can be adopted by the 700 members of GSMA, plus all the operators around the world on telco. That is the kind of approach that we need to take, whether it be in banking or even in federal government that we are talking about, right? Government agencies can adopt that, so on and so forth. We are also working closely with NIST to make sure that the standards, the quantum safe standards, are ready in time, and not just being ready, but there is a sandbox that's available where you can test that out and work it through, right? That is quite important. So the point behind all of this is we were quite confident that our algorithms will pass scrutiny, and we have incorporated them into these systems. But that's just one set of actions that we have taken. But if you say, so what should enterprises do, right? What should clients do? What we recommend is that everyone has to identify a champion it'll be their job. In other words, if you're serious about making yourself quantum safe, go name a person whose job it is to do that. Otherwise, it never gets the focus that it deserves. And one thing I failed to talk adequately about is that, let me see if I can go back and get to it. Oops, okay. Is that while 4 algorithms have been selected, you may say, when are the standards going to be available? NIST is working right now in defining the standards based on these 4 algorithms, and they're calling out that they will publish a standard sometime in the middle to late 23, and then it goes through an open review and update process, and after that, it's scheduled to be released sometime early in 2024. So there is a time frame now between now and early 24 where standards are not out yet, but we know what the standards are going to be based on. So we recommend that clients gain knowledge and work with a sandbox, and we provide a sandbox too, that you can go in and play with it so that you can see how those algorithms fit into your enterprise, your scenarios, and your use cases, how they perform. And if there are any challenges, then you can figure out how to work with them. Right? And then I talked about the government expecting an inventory for the agencies by May of this year. And so establishing a baseline inventory from a government standpoint is for a few reasons. One, you need to know how big the problem is. The second, you should be able to say, how much money do I have to allocate? Because nobody has budgeted for this, right? And you know that if there is no budget, nothing happens, right? But you got to figure out how big the problem is so you can budget for it. That's what the inventory and the baseline enables you to do. And then it also tells you or helps you prioritize what you need to go after. Because this may be a discovery process in many ways, in that enterprises may find out that they have crypto in places where they did not anticipate, or some of them are old, some of them they need not even remediate, or they can retire. So these kinds of decisions are made as part of the prioritization and development plan. So this is a simple 4-step plan that we recommend to clients to make sure that they become quantum safe as they get into this, and then transformation can happen based on the standards being released next year, and the ability for the enterprise to go execute them. Right? I know I've talked a lot about this. Now, if you really want to take a picture of this QR code, we just released an IBM Institute of Business Value white paper that has almost all of what I talked about, perhaps in a much more concise and descriptive manner, but didn't have the color that I had to provide, so you can probably enjoy that. Now, if you need more information, you can visit the IBM booth, and my evil twin sitting back there, John Viselli, who is much more qualified and much more intimate with this, can certainly talk about, because unfortunately I have to be catching a flight pretty soon, but he'll be around to answer any questions that you have. So with that, I want to thank the Q2B organizers for giving me an opportunity here, and for you for patiently listening to me. Thank you. Appreciate it.